We now come to the point where we introduce to you angles with Newton's laws. So in this case, given the right triangle, and given that this angle is theta, this angle will come into play later on when we talk about the weight. We know that the weight for any given object is going to go straight down. And so this is our weight vector. Let's assume that this problem has friction. So the friction will be going in this direction. And this friction will be one of two types of friction. If this is a first law problem, this is static friction. If this is a second law problem, this would be kinetic friction. For now, we'll leave it as just plain friction. Because of weight, according to Newton's third law, there should be an opposite and equal reaction called the normal force. So I'm going to draw the normal force. However, the normal force is always perpendicular to the object. Now, we are dealing with both the x and the y axis at the same time. So in previous problems, we decided to go ahead and just focus on the x axis only or the y axis only. That is still partially true in this case. However, we must consider both cases and not ignore either case. So we begin with this first idea. We could put the x and y axis like this, but you'll note that the only force that ends up being on any of the axes is going to be the weight component, the weight vector, which means that my normal force is going to need a sine or a cosine, and my friction is going to need a sine or a cosine. So for us, that means more work. If instead we put our x and y axis like this, tilted at an angle, you'll notice that the normal force is on the y-axis, the friction is on the x-axis, and the only one I have to worry about is the weight not being on the either x or y-axis. So that means less trigonometry for us, which is better. So if we do this, we have to focus on this weight vector. And according to trigonometry, we can go ahead and break this up. Starting from this point and getting to this point, we can do the following. We can go down this street and then make a turn. If we take this shape and kind of turn it around for a better view, I get this. Now note we made a right angle right here. So that right angle is actually right here. And may I propose to you that this angle theta, originally of the incline of the plane, ends up being the same as this angle right here. So in other words, this is the same angle, theta, and again by means of geometry. So this is the triangle I'm working with now. Now recall that this side right here on the y-axis becomes this side right here. Because this blue side is on the y-axis, I'm going to call that wy. In other words, that is the y component of the weight. And therefore, this one is going to be the x component of the weight. And that's because this x component is parallel to the x-axis. And essentially, if we wanted to, we could copy and paste this. We could take this vector, this x component of the weight, and we could go ahead and transfer it up here, and it would line up exactly on the x-axis. So this is the x component of the weight. We now employ basic trigonometry. So if I'm using this angle here, sine of theta is going to be the opposite over the hypotenuse. And therefore cosine theta, in a similar fashion, is going to be the adjacent, which is wy, over the hypotenuse. And you might be thinking, Mr. Over, didn't you switch your x's and y's around? Well, remember, where did this triangle come from? Right? We traditionally do trigonometry problems looking like this. However, in real life, we are looking at a trigonometry problem that's at this orientation. So this is where it came from, and you would recall that this component of the triangle is on the y-axis. And so when we turn it around, that y component ends up looking like a horizontal, when in reality, from the original problem, it was a vertical. We can multiply both sides by w. Same thing with the cosine on the bottom. That cancels out those w's. And now I get the components of the weight. So I have wx is w times sine theta, and wy is w cosine theta. Now remember that weight is mass times gravity, so we may express this at the end as follows. All right, let's go ahead and set up Newton's laws. Let's set them up assuming first law for now. So we're going to demonstrate both of these. For the x-axis, I'm going to assume that going to the right is positive and going to the left is negative. So as far as we're looking at this problem, you have this wx component, which is going to the right, right? I mean, I just copied and pasted from here, so wx is going to the right. And I have friction opposing that. Now remember, when we set these things up, if it's first law, we accumulate all of the forces on the left side of the equals, and we allow the right side to be equal to 0 to show the concept of balance and equilibrium. Okay. Now wx, we shouldn't write that. We should technically write w sine theta. And technically, to be even more technical, we could write m times g times sine theta minus f equals 0. And we could still be more technical. However, there's some technicalities. So I'm going to keep that equation on pause for now. For the sum of the forces along the y-axis, I'm going to assume up is positive and down is negative. So I have the normal force going up, and I have the vertical component of weight going down. That's wy. Now wy, we said that's w cosine theta. And we could rewrite that as follows. Now something interesting about this is if I go ahead and move this whole term to the other side, I get that the normal force is m times g times cosine theta. So remember we made a big deal about friction and about the normal force and about Newton's third law and opposite and equal reactions, and we said that as long as an object is sitting on a flat horizontal surface, that the normal force equals to the weight. However, as soon as you begin not being on a flat surface, as soon as you begin having an angle of inclination, then that normal force becomes smaller. And what is that normal force really? It's equal to the opposite and equal reaction in this case, which is m times g times cosine theta. So normal force is no longer weight. The normal force is this thing. Let's go back to this equation that we set up for Newton's first law along the x-axis. By definition, friction is mu times the normal. But what is the normal force? It's not the weight anymore, it's this thing. So I can rewrite this equation with this put into place. And so where I'm saying that right now is I have this equation right here and I have this equation right here. However, we don't really need this equation anymore because we went ahead and incorporated it into the setup that we have for the x-axis. So this is a problem that we've done in general that we set up for first law. How would this be different for second law? Well, the only real difference that we would have is that this wouldn't be 0, this would be m times a, and this would be m times a. And that's pretty much it. That's the only difference. That's the only difference. And that's because if this were accelerating, and I'm sorry, I should make another difference here. This would be a kinetic coefficient of friction. Whereas for first law, that would have been static. So make sure you keep track of your static and kinetic frictions. So this is kinetic because of second law. Consider that if this is second law, on what axis is this box accelerating? On what axis is this box moving left and right? It's moving left and right on the x-axis. The y-axis is not moving. In other words, this box is not jumping up and down. It's sliding down along the x-axis, which we've indicated to be in this direction. It is not sinking itself into the plane. It is not launching itself off of the plane. It is going down the plane along the x-axis. So as a result, our y-axis remains the same. It remains 0, and that remains in balance and in equilibrium. So the only change for second law is this would be m times a along the x-axis, and instead of static coefficient of friction, I would be using the coefficient of friction that's kinetic. Okay. So again, this is a general setup. There were no numbers given or included on purpose. We will do some more, and I'll have you work on some of those later, of course. Some big takeaways: sines, trigonometry, right? Sine and cosine, assigning positives and negatives appropriately, accounting for all of your forces on a free body diagram, keeping track of the x-axis, keeping track of the y-axis, being able and ready to set up Newton's first law and second law, being able to do the algebra, being able to conceptually give reasons and prove that what you're setting up is making sense, and then being pretty handy with the algebra. These are classic problems that are typical of free response questions on the AP test.